Good afternoon, everybody. Welcome to another wonderful afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. Hi, everybody. All right. So I think it was sometime this morning, I'm not exactly when, I sent out an email that had a link to a private YouTube video for test 2 answers. So if you want to see it again, or if you missed it, you can use that link. It's private. You can't go to my normal YouTube channel, and you can see test number 2 answers. All right, let's get back to work. Now, on Monday, I talked about acid hydrolysis of an ester. And we went through some examples. Let's do one more, because they're fun. Now, you know I'm an organic chemist. And the general reaction was remember, H plus is an acid catalyst. There are many acids. And what you get back is the carboxylic acid plus the alcohol you would have used to make that ester. Oh, let's have some fun. And the question would be, what 2 products would you get if you react this molecule? By the way, this is a cyclohexane ring, not a benzene ring. That I forgot to put it. I could have done a benzene ring, but I thought this would be more fun. So, what would be the products when you react that with acid and water? And don't forget, tonight I have my office hour from 6 to 7:15 on Zoom. If you have any questions, stop by. If you don't have any questions, stop by and say hello to Dr. White. And please be patient. I try and give everybody time to finish. Did I tell you next Monday is all students turn on your webcams day? I just made that up. Anyways, let's do it. All right, what do we have? We're starting with carbons, carbonyl, oxygen, and carbons on this oxygen. We have an ester. We're reacting it with acid and water. And what you get back is the carboxylic acid plus the alcohol you would have used to make that ester. What's our cyclohexane ring? What's our prime isopropyl? Remember, the carbon with the oxygen here is the carbon with the hydroxyl group here. Again, the carbon with the oxygen here, an R prime, will be the carbon in R prime with the hydroxyl group. With that in mind, R is cyclohexane. I get this carboxylic acid, and R prime, this carbon is this carbon, which will have that alcohol. And that's how you do it. Now, I mentioned earlier, but I'll mention again, we will come back to this reaction because that's how your body breaks down fats and oils. And I worked for a company that also took fats and oils, and I'll teach you another reaction to do the same thing later on in the semester, that makes carboxylic acids and alcohols. And that company did it to the tune of about 2 to 3 million pounds a week. Yes, 2 to 3 million pounds a week. All right, let's move on. Well, if you can treat, or another way of saying react an ester with acid and water, what about base? Now, this reaction is called saponification of esters. It's a key organic reaction. Oh, you say that about everything. And it was used to make bar soap. And we'll get into that later in the semester. Yep, we'll get into soap and a whole lot of other neat things. And I'll stick to one base. Better yet, yeah, I'll stick to one base for now. You could have other bases, and all you do is change the cation. But, you know something, let's expand it. Let's have some fun. And if you take a base, hydroxide base, MOH, you can use other bases, but for this class, let's stick to either M is sodium, lithium, or potassium, water. And what you'll get is not the carboxylic acid. You'll get the carboxylate anion of the carboxylic acid you would have used to make that ester plus the alcohol. And why? Because if you first get this, and the stuff underneath them, you don't have to write down. Dr. White's is having some fun. That you know a carboxylic acid will react with any base. And the fastest reaction in all of chemistry, called the Eigenblick, which means in a blink of an eye, really faster than that, is an acid-base reaction. So that's why, and you got to be sure you don't get the carboxylic acid, you get the carboxylate anion plus the alcohol you would have used to make that. And let's look at the following. If you took the following reaction, what two products would you get? Well, what's different here? Well, carbons. Ooh, carbonyl, carbon double bond, oxygen, oxygen, more carbons, R prime. Ester. What's LiOH? Lithium hydroxide. It's a base, MOH. Water, well, you know what water is. And remember, M can be lithium, potassium, or sodium. Doesn't matter which order you write it. And you get not the carboxylic acid, but because you're in base, you get the carboxylate anion of the carboxylic acid you would have used to make that ester plus the alcohol. Remember, the carbon in OR prime is the carbon in R prime here that has the hydroxyl group. This is R prime, And those are the two products you go, oops, bad Dr. White. I had almost made a mistake. I looked and said, whoa, wait, that's wrong. Now that's correct. Now you don't have to put the charges down, but I always will. And that's how you do it. And it's your turn. What two products do you get when you react that molecule with potassium hydroxide, KOH, and water? One of these days, I'm going to have a recording of that game show music. When they ask a question, you hear da 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 da, whatever. Nah, I won't. All right, let's take a look at this. We look at the starting material. What's different? Ooh, carbonyl, oxygen. It's the same carbonyl carbon. On the oxygen, I have carbons. On the carbonyl carbon, I have carbons. And ester. I'm reacting it with a base, hydroxide base, and water. M can be sodium, potassium, or lithium. There are other bases, but I'm going to stick to that for this class. And what do you get? Pay attention, Dr. White, don't make a mistake again. The carboxylate anion of the carboxylic acid you would have used to make that ester plus the alcohol you would have used to make that ester. What's our isopropyl? What's our prime and propyl? Therefore, here's my R group, carbonyl. Be careful, Dr. White. I am. Oops, not M plus. M here is potassium. And then my alcohol, R prime, 3 carbons. The N carbon has the oxygen there. We'll have the hydroxyl group. And that's how you do it. Now, as I've mentioned, well, here, I'll give you a chance to look in case you didn't see if your answer is right. Oh, no, don't look. Naked carbons. Now you can look, they're fully hydrogenated, not hydrogen. They're clothed. All right. As I mentioned, there'll be a couple of synthesis problems on test 3, just like on test 2. And the question is, what molecule do you react with sodium hydroxide and water to make those two molecules? Your turn. Remember, you're learning the building blocks of general reactions that organic chemists use to make things in our daily life. And Mother Nature uses them too, to allow your body to do things, and plants and animals to do things, to keep them alive, which is a good thing. All right, I think everybody's done. So what do we react with sodium hydroxide and water, which I can write like this as a base and water, where M can be, in our case, it is sodium, but it could also have been potassium or lithium. And what do we have here? Ooh, a carboxylate anion. What do we have here? Ooh, oxygen and a carbon and alcohol. And what do we react with base and water to make these two compounds? An ester. So what's our methyl? What's our prime? T-butyl. Therefore, R is methyl. I'll have my carbonyl, oxygen. The carbon with the hydroxyl group will be the carbon with the oxygen in R prime, T-butyl group. And that would be the ester you would react with sodium hydroxide and water to make this carboxylate anion and this alcohol. That was fun. But then I'm a synthetic organic chemist. All right. You notice this next reaction, I got a big smile because Dr. White's really happy. And what is that? And there's a mistake here, not for me, but for you. There should be a 2 in front of that. And here we have an ester. First step, we're reacting with not 1, but 2 Grignard reagents. Second step, acid and water. And the beauty, and I mean it is beautiful, of this reaction, you make not 1, but 2 carbon-carbon single bonds. And you get 2 molecules, 2 alcohols. Now, first of all, let me rewrite it. Now, at my level, we don't put the 2 in there because everybody knows it should be there. See, organic chemists are lazy when we can be. But for this class, I will. Keep your eye on the carbonyl carbon. What's directly attached to that is still attached, R. You have a hydroxyl group And then from your Grignard, remember X can be chlorine, bromine, or iodine. You make not one, but two carbon-carbon single bonds. But what about this? It gets kicked out. Notice how violent we are. Gets kicked out to give that second alcohol. Now, I'm going to show you a mechanism. It's one of the few times this will not be on a test. This attacks this and kicks that out. And now you have a ketone, and you know a ketone reacting with the second molecule of the Grignard will make an alcohol. And this, remember, second step, acid and water. And here again, second step, acid and water. This is a very strong base. Add acid to it. You'll protonate it and get the alcohol. So the stuff underneath here, I just thought I'd show it to you because it's fun. I wish I could do more of these, but I don't have a chance. And because it's a one semester, I'm not going to ask you what's the mechanism on a 2 semester. You get questions like that. So let's look at this again. See, I forgot the 2 because I'm a lazy organic chemist. On test, I don't. Here we've made our 2 carbon-carbon single bonds. Very special, very rare, very good. And this part gets kicked out for this alcohol. So let's take a look at this. Oh, and I should say the carbon in the R triple prime is the carbon in the R triple prime bonded to this carbon. The carbon in the R triple prime with the MgX on it is the carbon in R triple prime bonded to carbon with the hydroxyl group. And let's take a look at this. What do we have here? Ooh, an ester. This is R. This is R prime. What do we have here? Ooh, 2 of a Grignard. Second step, acid and water. And keep your eye on the carbonyl carbon because that's where the fun is. And that becomes an alcohol. What's attached to it, R, is still there. And you make not 1, but 2 carbon-carbon single bonds. And then this becomes this alcohol. So you're making 2 alcohols. And if we look here, what's our triple prime? That part of Grignard. So I have my carbon that was the carbonyl alcohol. R is methyl. And then my 2 Grignards where I make 2 carbon-carbon single bonds. And I get a second alcohol from R prime. And that's what you get. Now, when you do this reaction, you try and keep R prime very small so you can distill off the smaller alcohol and purify it to get the larger alcohol. But look at this compound. In one step, with a very simple ester, a very simple Grignard, I've made a very complex molecule. And that's a good thing, and it's fun too. Now, as a special gift to you from me, Dr. White, don't tell anybody I'm being nice, ruin my image around here, but I will never give a synthesis problem with this. I can do them, but I think it's too hard for you and it's not fair. And the question is, if you react that molecule, first step that reagent, second step acid and water, what two products do you get? Oh, is this going to be a fun answers? Or pretty really not fun. And the votes are coming in. And everybody's done, so I better get to work. If we look at this, what's different, what's not carbon, what's not hydrogen should get your attention like that. And I have an oxygen, double bond this carbon, another oxygen. There's carbons on the oxygen, I'll call R prime. There's carbons here, I'll call R. I have an ester. I look up here, carbon, magnesium, bro. What do I have here? R prime. I have a Grignard. If we take an ester and we react it with 2 molecules or moles of a Grignard, remember X can be chlorine, bromine, or iodide. And second step, acid and water, we'll get, keep your eye on the carbonyl carbon, what's attached to is there, comes an alcohol. From the Grignard, we make not one, but 2 carbon-carbon single bonds, and this part of the ester gets kicked out as an alcohol. So, this is our triple prime. I have my R group. That was the carbonyl carbon, now the alcohol carbon. And then what's R? Isopropyl. The carbon with the Grignard is the carbon bonded to that. We'll do 2 of them. Whoa, is that amazing? And this part gets kicked out to this. R is methyl. Look at that. Oops. Is that an amazing alcohol? Really complex. And in one simple step, with a simple ester and a simple Grignard, we've made a very complex molecule. And the alcohol from the ester R prime OH, you distill off. And that's the beauty of this reaction. Oh, I've got to do one more. This is too much fun. Oops. And what two things would you get when you react that molecule, step one, with that molecule, step two, acid and water? Your turn. Ooh, fancy new sign. Your turn. Oh, I like that. It's like some of you are getting really good at this. That makes me happy. And make you happy too, I'll bet. By the way, it's permitted to smile in my class. Wow, everybody's done. All right, what do we have here that's different? Carbonyl, oxygen, carbons, carbons, ester. This is R prime. Ooh, carbon, carbon, magnesium halide, two of them, a Grignard. Remember, X can be chlorine, bromine, or in our example, iodine. Second step, acid and water. Keep your eye on the carbonyl carbon. What's attached as attached to it comes in alcohol. Then you make not one, but two carbon-carbon single bonds from the Grignard, and this part gets kicked out to another alcohol. What's our triple prime? Ethyl. So I have this carbon, alcohol, what's attached to it, R, is still attached to it. Then my R triple prime, you make not one, but two carbon-carbon single bonds. And then my alcohol, R prime, is methyl. Oh, that was fun. It's always fun to make really complex, nice molecules. But now you really know I'm a synthetic organic chemist. Now, one of the things you should always be asking is, why am I learning this stuff? What good is this for me? Well, the obvious answer is someone told you had to take this class and you want to get a good grade so you can get into a program or a school. And that's why. Well, why learn this stuff? Well, let's look into something. Let's talk about polyesters. Poly means many. I'll never ask this on a test. And mer, units. And these are many esters linked together. How many of you have ever seen a train, a box freight train? I hope you all have. By the way, Dr. White's a model railroad enthusiast. I love railroads too. When I was in Europe on a Saturday, I'd go to whatever city I was in, go to the Central train station like Amsterdam Central. And on a Saturday afternoon, I'd sit in the main train station and just watch the trains come in and out. Yes, I'm a train lover. My father was too. He used to take me to the south side of Chicago where they had back then it was steam engines. Oh, what monsters. They were beautiful. But anyways, Think of an polyester, many esters linked together like boxcars in a freight train. Now, let's look at this one specific one. This is a dicarboxylic acid. Di means, and this is something I stayed away from, two functional groups, actually in this case, three counting the benzene ring, in a molecule. And if we react it with ethylene glycol, what do you get? Now, what I'm going to write on the whiteboard, you do not have to write down. This will not be on a test, but it helps answer the question, why are you learning this? Take a carboxylic acid, alcohol, acid catalyst, you'll make an ester. And this is ethylene glycol. And it has not one, but two alcohols. If I were to react it, I have my carboxylic acid, my alcohol. This carboxylic acid does not react. This one does. Again, you don't have to write this down. I have this new ester right here. But if you look here, I still have an alcohol. On this side, I still have a carboxylic acid. So I could react this with more terephthalic acid. And I have this alcohol reacting with this carboxylic acid, and this reaction I'm slipping toward the floor. Hold on. That happens in a classroom too. Now, this new molecule, I have a carboxylic here acid that can react with more ethylene glycol. I have it here, and it can keep on going and going and going, like the Energizer bunny, bang, bang. Anyways, not to bring commercials into my class. Well, when you have that repeating unit, we can use brackets. And when you react it, this is the molecule you get. This is my repeating ester. And N, how large can N be? 1,000,000. Now that's long. Now this compound has a name. It's a common name. Remember, I'm going to do something right now. Polyethylene terephthalate. Remember, phthalic acid, you drop the IC in A acid and add ATE for an ester. Well, this is called polyethylene terephthalate. Polyethylene terephthalate. That's a lot to say. Polyethylene terephthalate. Hold on a second, I'm getting thirsty. That's a lot to say. Polyethylene terephthalate, make me thirsty again. And why are you learning this stuff? Well, if I'm lazy, I don't want to say polyethylene terephthalate, I can say PET. And when you take terephthalic acid, ethylene glycol, you get PET, which is the plastic in my water bottle. Why do you learn this stuff? Because these reactions, like this one, making an ester from a carboxylic acid and an alcohol, are used in our daily life to make things, such as my water bottle. If you look on the bottom here, it says PET. That's why we're doing this stuff, because we make things. What? My bottle, and the rest of the semester, I'll teach you more things we make using these reactions. Oh no, guess what? We finished this chapter. So you know what it means? Two things. One, next Wednesday, I will go through the carboxylic acid and ester problem set. Next Wednesday, I will go through the carboxylic acid and ester problem set. You should do it before that. That helps you get a good grade on my test. And you know what else it means? It's new functional group time. Now I have to warn you, if it looks like I'm having way too much time in this new area, I am. Why? Because it helped pay my mortgage and a lot of other things for many years. And I have 9 US patents in this area. So do I know this stuff? You better believe it. Do I have fun with this stuff? Yes. And I have to open up let me close this chapter. And let's talk about chapters, if you're reading the book, which you don't have to, but if you were, 11 and 13. And this deals with amines, amides, and heterocyclic compounds. And this chapter, coming attractions, I'll teach you how to get your clothes nice and soft. And I'll also teach you, if your towels aren't as absorbent as they used to be, how to get them absorbent again so they work like they're brand new. And then on a not that nice note, I'll talk about one of the dumber things I've done in life. And luckily, because I'm an organic chemist, it wasn't as dumb as it could be or harmful to me. All right. Now, what's an amine? Amine, and the switch is off for this slide. Amine is an organic derivative of ammonia. Ammonia is NH3. And amines are where you replace the hydrogens with carbons, alkyl, cycloalkyl, aroamines, benzene rings. Oh, and I'll also talk about what's the best mouthwash to keep your gums and everything free of problems. And I'll also talk about stuff they use in hospitals. Wow, we're going to talk about a lot of stuff. Now, when we talk about nitrogen and ammonia, nitrogen has 5 valence electrons. Here's the Lewis structure. And normally to get an octet, nitrogen has 3 bonds. Unlike carbon, which has 4, nitrogen has 3 bonds. But this non-bonding pair of electrons, which I usually call the lone pair of electrons, can also bond. And what that means is, I don't have it here. And this you should remember. Nitrogen can have 3 or 4 bonds to it. And that's different from carbon, which always has and only has 4 bonds. Nitrogen can have 3 or 4. Makes it interesting. Now, switches off for this slide. But I'll use this terminology. This is a primary amine. This is a secondary amine. And this is a tertiary amine. Where R can be the same or different. Now, in amines, you have 3 bonds to nitrogen. Which is why 1 R group plus 2 hydrogens makes 3. In secondary amines, you have 2 R groups, so 3 minus 2 is 1 hydrogen. And in a tertiary amine, 3 minus 3 is 0. Why? There are no hydrogens. So in amines, you have 3 bonds to nitrogen. Now, something near and dear to my heart, I mean really near and dear, is I have a couple of patents, and this was my first US patent. When you have 4 bonds to nitrogen, one of the electrons and one of the bonds comes from the nitrogen, not sharing. So that means it will have a plus charge. And because all molecules have a net 0 charge, you need an anion. For this class, I'll keep it to the halogens, where X equals chlorine, bromine, or iodine. Now, I'm going to try and be, this actually should be ammonium. I never noticed I had a mistake on that slide. Quaternary ammonium salts, and I'll only say it once, and I'll try and be a good boy, and that is, if you work with quaternary ammonium salts, and I'm a world expert in these, I have 9 patents, and most of those are with quaternary ammonium salts. We call them quats, Q-U-A-T. But for you, I'm going to use the full name. And quaternary ammonium salts, where are they used? Fabric softeners. The key molecule in a fabric softener is a quaternary ammonium salt. And other quaternary ammonium salts make amazing antimicrobial compounds. And those are used in places like hospitals. And they played a role in disinfecting operating rooms during COVID-19 and before that. And Dr. White loves quaternary ammonium salts. They've been good to me, I've been good to them. Again, switches off on this slide. Now, how do you name them? Oh, I looked at the clock. It's time for a break. Let's take a 5-minute break. I can get up and stretch, and I'll see you in 5. All right. First, a public service announcement from the management, me. Don't forget, tonight from 6 to 7:15, I have my office hour. If you need any help with anything, stop by. I'll help. If you can't stop by and you really need help, email me and I'll see on Thursday or Friday if I can set up a private Zoom meeting with you. Because I want all my students to do well in this class. All right, don't forget the hand-in labs. Some of you haven't. It's going to hurt your grade. And that's the second public announcement. And something else, in a little while, we'll have a Dr. White show and tell. I don't know if I told you this, but when I was in grade school, we had show and tell in English. The teacher was scared of me because she didn't know what I'd bring in. Usually it was something very scientific that she had no idea what I was talking about, but this won't be that case. Let's get back to amines so I can have some fun. Now, when it comes to nomenclature of amines, nobody who works in amines uses IUPAC unless you have to for a legal document. We use common names. And for amines, you list the alkyl groups or cycloalkyl attached to the nitrogen and then add the word amine. It's that simple. So let's do some. And if we look at this, the question is, what are we dealing with? What functional group? Well, you look for what's different. What's not carbon, what's not hydrogen, get your attention like that. Ooh, a nitrogen. And we have a primary amine. You don't have to know that, but I'll use the terminology. How do you name that? Common name. Ethyl amine. That wasn't that hard. Let's have you try one. And what would be the common name of that compound? Now, in test 3, unlike where I've always said do the common or do the IUPAC name, I'll have do the IUPAC or the common name. And the question you should be working on now is, what's the common name of that molecule? All right, my turn. And we look here, what's different? Ooh, a nitrogen. I've got carbons on that nitrogen. A primary amine. I'll never ask you what's a primary, secondary, tertiary amine, but I'll use that terminology this chapter. Now, how do we name it? We name the R group that's on there, and that's an isopropyl group. And add the word amine. Now, let me introduce you to an old friend of mine from graduate school. This is a molecule I used a lot in my research to make a special base to use in making special enolate anions. And remember, 1, 2 is di, 3 is tri. And what would be the name of that molecule? Common name. And say hello to my old friend. Now you know I'm an organic chemist. I say molecules are my friends, and they are. And notice there's 3 bonds to nitrogen amines. That's why there's 2 alkyl groups and 1 hydrogen. And how do you name the common name for this? Well, what are the 2 R groups? This is a secondary amine. And in this case, R and R prime are the same. So this is di-isopropyl amine. And I used a lot of diisopropylamine in graduate school for my research. Now, one thing that we don't do, well, we can, but I stayed away from in up to now, but I will do. Another way of writing this would be this. And these are the same molecule, diisopropylamine. This tells you there are 2 isopropyl groups on the nitrogen. Well, in that case, let's try this. What would be the IUPAC name, not the IUPAC, the common name for that molecule? Remember, 2 is di, 3 is tri. I see the votes are coming in. I'm looking over here where I have something you can't see, but I can. How many people out of the class have said yes? We're face to face. I could just look around the classroom and everybody would be looking up at me when they're done. Or I'd say, look up and smile when you're done. And you can do that now too, if you want. All right, let's do it. What do we have here that's different? Nitrogen. Ooh, it's got not 1, not 2, but 3 methyl groups. 3 is trimethyl amine. Now, on a test, if you ever have to draw trimethylamine, either one of these is correct. On a test, my software likes to do that, so get used to it. Now, let me show you why, and something interesting that we won't have on our test. why organic chemists who work in the area, like me, don't use IUPAC names unless we have to, like for legal documents. If we look at this molecule, how would you name it? Common name. And since there's a common name, there's no rules which goes first, alphabetical, but this is N-butyl methyl amine. Now, for the IUPAC, this is common. Remember IUPAC, which stands for International Union of Pure Applied Chemistry, the official name. You find the longest of the two chains. And that would be butane. Drop the E, add the word amine. Which carbon close to the end of the chain has the nitrogen? That would be 1. Now, notice this methyl group is on this nitrogen. If I had put methyl in front of there, you'd think it's on the butyl group. To tell someone it's on the nitrogen, we use the capital N, then the name of the alkyl group. So it's N-methyl 1-butanamine. Which is easier, N-butyl-methylamine or the IUPAC? And the answer is, for me, common. So I will never ask on a test or the final IUPAC nomenclature for amines. Now, let's look at quaternary ammonium salts. And one of these days, I'll make up a slide. I get lazy. I'm a lazy organic chemist. Remember, a quaternary ammonium salt has 4 R groups. You don't have to put the charges, but I will. And here we have this molecule. And how do you name it? Name each R group as the alkyl group it is in the front, like you did with amines. But where it's different is, and add there are other anions, but I'm going to stick to the halogens. Add the words ammonium halide at the end. Now, what does that halide mean? Well, watch. Cl- is chloride. That's what we mean by halide. Br- is bromide. I- is iodide. And that's how you do it. So if we were to take the following molecule, how would we name it? What's different? A nitrogen, but we have a positive charge and an anion. And I should point out, the bond, even though we write it on the right here, this bromide, anion, is ionically bonded to the nitrogen, not this carbon. But notice I have two methyl groups and two ethyl, diethyl, dimethyl, ammonium, and the anion, Br minus, is bromide, so it'd be bromide. And that's how you do it. Now, I could have written this. Notice there are two methyl groups on the nitrogen, two ethyl groups. And you don't have to show charges, but I always will. And these are the same molecule. There are just two different ways of drawing it. And when amines and quaternary nitrogen compounds, we tend to do that, we organic chemists. So for quaternary ammonium salts, name the alkyl groups that are on there, then add the words ammonium halide. If it's chlorine, Cl minus is chloride, Br minus bromide, I minus iodide. And what would be the name of this molecule? Remember, 2 is di, 3 is tri. And what do we have here? We have a quaternary ammonium salt. Notice there are 3 methyl groups plus an ethyl, 4 groups on a nitrogen with a plus charge, and all molecules have a net zero charge, so we have an anion. And this would be trimethyl, ethyl, ammonium, and Cl minus is chloride. And that's how you do quaternary ammonium salt. Oh, I almost said the slang word QUAT. Oops. Well, I won't. All right. It's show and tell time from Dr. White. And I'll do a couple more during the semester, but you don't have to be scared. All right. personal thing. In my family, it's hereditary from my grandfather through my mother, my sisters, and I got it. Bad dental problems. And many years ago, I had a problem with my gums. And a dentist I had who was really great, unfortunately passed away. He was way older than I was. Prescribed this mouthwash that's in this bottle about this long, big, 700, no bigger than this. And it was like $70 a bottle prescription, but it worked. Well, anyways, he had to retire because of health problems, and unfortunately finally had a heart attack and it killed him. Sad. I love Dr. Rudnick. And I was in between dentists, and that stuff had run out, and I hadn't found a new dentist. What do? So I went to Walmart. You can go to any big box store, and they have a big aisle of mouthwash. And I picked up the Listerine and bought some because I usually don't use mouthwash at that time. And came home, used it, and the gum problems were so bad. If I were, ouch, yeah, it got bad. So the Listerine did zip, didn't help me at all. And I looked at the bottle of the mouthwash that was prescription. I saw, oh, it's a quaternary ammonium salt. And if I looked at Listerine, they used a phenolic compound, a benzene ring hydroxy group with an R group. And that has antimicrobial properties. But in my mouth, zip. So I went back to Walmart, and there are two main brands, Listerine and Scope. And Walmart, since Dr. White likes to save money, I'm not getting kickbacks for this, has their, where does it say here? Compared to Scope, meaning it's the same. And if you look on the back here, the ingredients, and I'll read it to you. Well, it's got water, alcohol, glycerin, flavor, a sweetener, salt, and a preservative, and this compound, cetyl pyridinium chloride. That's a quaternary ammonium salt. There's other ways of doing names on labels for mouthwash and other things. And I'll teach you about pyridine. And this is a quaternary ammonium salt. Cetyl is a common name for an alkyl group. Let me show you in case you're wondering. There's a structure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I already knew that. And this molecule has amazing antimicrobial properties. And lo and behold, I used it. No problems. I did find a dentist. He wasn't that good. Then about 2 years ago, I'd gone through a couple of dentists. I found through a recommendation of someone I know, a really great dentist I'm using. That's Dr. Thomas Angerame in Palatine. And if you need a great doctor, dentist, and his staff is great too, I mean, really great, and he's really good. Dr. Thomas Angerame in Palatine, email me and I'll send you the contact information for Dr. Angerame. And he's just a great guy. All his staff are really friendly and helpful. And I've had a lot of dental work because I have dental problems, and he's done a superb job. I really like him, as you can tell. And that's my show and tell. Why are you learning about quaternary ammonium salts? Because they're in mouthwash to help protect your mouth. Now, one of the things I found that the Walmart brand, which is a lot cheaper than the Scope, is equivalent. I wonder if they have Scope. It's called Toll Produce It, make it for them, and then they just slap on their own label. But it's about half the price of a bottle of scope, which is a nice savings. And with that, I think it's time for lab. So let's start today's lab. And today's lab is aldehydes and ketones. And as you know from test number 2, this is an aldehyde, and this is a ketone. And part of, as I've told you, my philosophy when I rewrote all the labs for this class, if we were in face-to-face, we'd be in the lab right now. I'd be telling you this, and then you go and do the actual experiments. But because we're online, I'll give you the data, but you still have to use the same thought process and understanding to answer questions, just like if you've done the lab. Now, first thing is solubility of aldehydes and ketones in water. And what you'll do is in a test tube, you'll fill it about 1 milliliter halfway up. DI water stands for deionized water. And in each test tube, you'll add about 5 or 10 drops of the aldehyde or ketone and mix it. Remember, pretend this is a test tube, you can either hold it very tightly and hit it 3 or 4 times to mix it. Do not tickle it. You really got to hit it good. Never ever mix a test like that. We also have the vibro mixers, which are the disc you push down on, and it goes a lot faster to my hand and mixes it, and they're fun to use. And if you do that, this is the observations you get. And hold on. I close this because all right, we're back. Now I just got to make you see it. And this is the results you get. Now, notice in red, under each one of these aldehydes and ketones in this table, draw the structures. So don't forget to do that. Now, the second part, odor, I just omit. I have it there. You don't have to do anything with this. But you've smelled benzaldehyde, you smell vanillin. All right, let's talk about the oxidation of ketones and aldehydes. And this is a reaction I didn't teach you in the let me just do something. Oops. Now, if you take an aldehyde and you oxidize it with potassium, oh, wrong lab. I think on this one, we're using potassium. Potassium dichromate, and it's acidic that helps it. You'll oxidize this to a carboxylic acid. Well, this is a orange, red color, reddish orange. My sisters always say, you don't know your colors. I know my basic ones, red, green, yellow, and blue, but some of the different ones, they're right. They know them better than I do. And when this is oxidized, this gets reduced. Hold on one second. I think I might be thinking the wrong lab. Which one did I use here? Nope, I was right the first time. I'm sorry. This will also do that, but for this lab in real life, the other one works better. Once in a while, even when I have different options, I forgot which one I use. I was right the first time. You use potassium permanganate, that's an oxidizing reagent. This is purple. And when this gets oxidized, this gets reduced to manganese dioxide, MnO2. And this has a muddy brown color. That's the best way I can describe it. Now, ketones cannot be oxidized. No reaction. This is purple. And it stays purple because there's no reaction. So if you take a molecule that you think is an aldehyde or ketone and it turns muddy brown, you know it's an aldehyde. If you take a aldehyde or ketone, react it with potassium permanganate and stays purple, you know it's a ketone. And I wasn't in screen sharing, so I apologize. Let's do it again. Somebody should have yelled out to me. I can't see that. All right, let's do this again. If you have an aldehyde, react it with potassium permanganate, KMNO4, it oxidizes it to the carboxylic acid, and the potassium permanganate is reduced to manganese dioxide, MnO2. That's muddy brown. Now, if you have a ketone and oxidize it or try to react it with potassium permanganate, it does not react, no reaction. So the solution stays purple. And this is a way of identifying an aldehyde from a ketone, which before organic chemists had all the electronic analytical equipment we have, like infrared spectroscopy and nuclear magnetic spectroscopy. That's how you could tell, do you have an aldehyde or ketone? Now, since the 1960s and 50s, we have that equipment, but still, these are important tests. And this lab, you can watch that on this YouTube, which I would recommend you look at it. And the lab, if we're in the lab, you'd take a dry test tube, add about 1 to 2 milliliters of the KMNO4, about 2/3 of the eyedropper for that bottle, add about 5 drops of the compound being tested. And this is the results. Now, to make it interesting, I have in the lab, and this one too, unknown number 1. Now, the district attorney of Kane County has come to us and say, I have a person who's done this. I think we want to prove that this heinous crime. I'll let you fill in the blank what heinous crime. And we took this evidence from the crime scene. And if it's an aldehyde or a ketone, we'll know, is this person guilty? So please help us out. And you run the test and you get it's muddy brown. You'll have to answer the question, is it an aldehyde or ketone? I'm not going to give it away. Now, The last part, oh, I wish we were in a lab face to face, is a fun reaction. And that's making what's called a crossed aldol condensation. Now, here's the overall reaction. I have forgotten here. We do it, the solvent is ethanol. And you take acetone, this ketone, that's a common name for 2-propanone that nobody ever uses, and notice it has not one, but 2 alpha carbons with hydrogens. Now, if we look at this, and the reason why it's called Ross aldol, because you're not reacting it with itself. You're reacting, in this case, with an aldehyde. Now, if you look at benzaldehyde, that's why we have the 2 here. Here's the alpha carbon, and there's no hydrogen on the alpha carbon, which means that can't form an enolate anion. And it forms this very impressive molecule, dibenzyl acetone. Now, let's go through the procedure, and then I'm going to have fun, because this is one of the rare times I get to show you a full mechanism. Yay! All right, what you would do in the lab is add 1.3 milliliters of benzaldehyde, 0.5 milliliter acetone, and 7.5 milliliters of ethanol in an Erlenmeyer flask, which you swirl like this. Then you'd have 2.5 milliliters, 2.5 milliliters of 5% aqueous, that means water, solution of sodium hydroxide. And you got to keep on swirling clockwise or counterclockwise for 5 minutes until you get a solid. Now, you'll cool the mixture in ice bath and collect it on what's called a Buchner funnel. And let's see if I can get you one. Look at the on the top here, hold on, let me make sure you can see it. See this white porcelain right up here? That's called a Buchner funnel. It has holes in it. And then this is a Erlenmeyer with a sidearm. You have an adapter. We use a cone adapter. And this sidearm, here we have hooked up the vacuum pump. The labs at ECC, each one has vacuum connector to big pump in the back in the storeroom. And what you do is pour in the top here, your liquid and solid. There's a filter paper in there, and the liquid comes through, but the solid stays on the filter paper. And this is a way of separating a solid liquid. And hold on one second. I'll be back in about 30 seconds, maybe a little longer. Hold on. Wow, a second show and tell. In my living room, I have a couch table with a lot of glassware and chemicalware that have been nice and I purchased over the years. And here I have a Buchner funnel. Now, you know I'm an organic chemist. See the holes in there? You put a piece of filter paper in there and you have it hooked to that Erlenmeyer with a vacuum, sucks the liquid through, and on the filter paper, you collect the solid. You let it sit there for a while and it'll dry off the solid. And you do that for the slab. And then you take the melting point. And here, if you were in a lab, that would be the melting point. Remember, since you're new at taking melting points, your melting point is always going to be a little lower than the literature value. Now, let's take a look at how do we go from this very interesting common name dibenzyl acetone. And this is what you're seeing on the screen. Pay attention. If we start with our two aldehydes and the acetone, react it with base, one of the alpha protons from the acetone forms this enolate anion. That's the key reaction, because this now in an aldol condensation attacks the benzaldehyde carbonyl to form this aldol product. Now, what you don't know, but I'm going to teach you now, is when you can have conjugation, alternating single, double, single, double, single, double, and so on bonds, that makes a molecule more stable. And anything a molecule can do, if it's make it more stable by losing another stable part of the molecule, it can. And if you look at this molecule right here, got a hydroxyl group and a hydrogen on adjacent carbon. And if I lose, let's see, H and H and O, H and H and O, H2O. Well, if I lose this hydrogen, this hydroxyl group, I'm losing water, and between those two carbons, I form a double bond. And notice this double bond now in the benzene ring is conjugated to this double bond we just made, which is conjugated to the double bond of the carbonyl. So that makes it stable. But we're still floating around in base, and the other carbon, alpha carbon of this carbonyl, I can form an enolate anion. I do. It attacks this second aldehyde to form this aldol condensation right here. And once again, if I can get conjugation alternating single, double, guess what? If you can lose a stable molecule, it will do that. H here, OH, water. Between these two carbons, I form a double bond. And now this double bond is conjugated to ring to the carbonyl. The whole molecule is conjugated. And that's how you make it. Now, the key step again is the first step. The acetone, CH3, carbonyl, CH3, forms this enolate anion right here. Now, interesting thing about dibenzyl acetone, if you look at this, this is a nice bright yellow compound. Why is that? Well, when you have a lot of double bonds conjugated, it absorbs some of the light, certain frequencies of light. In this case, with dibenzyl acetone, if you have white light, like in my room or in the lab, all the colors except yellow are absorbed, and that's why it seems yellow. And I'll talk later on about other dyes. And for this lab, you'll have questions to answer. Now, where I have this question, what did you learn about the relationship of aldehydes and ketones and their odor? Omit. You don't have to do that. It says it on the paper. And you have only 3 questions. And with that, I'm done for today. We're done for the week. unless you want to stop by and ask questions tonight at my office hour from 6 to 7:15, or you just want to stop by and say, hello, Dr. White, that's allowed too. And with that, I'll remind you, next Wednesday, I will be going through the carboxylic acid and their derivative, mainly ester, and carboxylate anion problem set. Work on it. Don't fall behind, please. And with that, I'll say in Yiddish, which means go in health, gehen gesund, and I'll say goodbye. And I stole that from Granny the Beverly Hillbillies. Bye, Alvaro. Bye, everybody.